So a homomorphism is something that goes from one group to another. And it's a map of sets which has the property that it takes one multiplication into the other. So f of g times h is f of g times f of h, where this multiplication takes place in g, and this multiplication takes place in g prime. So analogy is like a linear map between vector spaces. It takes the addition in one vector space to another. It takes scalar multiplication to another. Now, some simple properties of homomorphisms which you establish in the homework is that it always takes the identity to the identity. And if you apply it to the inverse map, G inverse, that happens to be the inverse of f of g. So once you have this property, this is the only thing you need assume. I mean, you'd want all of these properties if you preserve the group structure. But once you assume the property that it takes one multiplication into the other, it immediately follows that it takes the identity into the identity, and it takes inverses into inverses. To prove that it takes the identity into the identity, you use the fact that in a group, E times E is E. E is the only element which has that property. No other element has the property that A times A is A. Okay, this is a unique element with that property because you could cancel E by multiplying by E inverse. So if you take that and you apply F to it, you get F of E times F of E using this property. That's F of EE. So maybe I should have written that down. F of EE, which is F of E times F of E, is equal to F of E. Applying F to both sides of this identity, and then using the homomorphism property. And then we see that F of E has that property in the group G prime. So multiplying by F of E inverse, you see that F of E is E prime. Okay, you guys did all this for homework. Same thing, I'll let you do the inverse one yourself. It's from the unique property of inverses. Now, some important things about homomorphisms is that if we could have another homomorphism to G double prime, and the composition H of F of two homomorphisms is a third. And we're going to see that a lot today, that when we compose two, because if you have this property for F and you have this property for H, you'll see that you have this property for the composition of two. Some important subgroups that are associated to a homomorphism, you have the image. Peter defined last time, so that's the set of elements of G prime, which are equal to F of G in G prime. So they're the things that are hit by the homomorphism. And that's a subset of G prime. And you have what's called the kernel. And for those of you who've done vector spaces, you know this sort of thing. That's the set of G such that F of G is the identity element in G prime. And that's a subgroup. That's a subset of G. Just like you have the kernel and image of a homomorphism of vector spaces. And if both of these are the trivial element, if the image is, so if image is equal to G prime and the kernel is equal to the set E, which is always in the kernel, the image always contains E prime by the fact that F of E is E prime, and the kernel always contains E. So if the image is G prime and the kernel is E, we say F is an isomorphism. And if beyond being an isomorphism, if G is equal to G prime and F is an isomorphism, we say F is an automorphism, an isomorphism from G to itself. We'll give some examples of that. Now, I think in homework you showed that these are both subgroups of a group. Is that right? Both subgroups.